In this video, we want to talk about and read the paper called Sample Selection for Fair and Robust Training, which was published in NeurIPS of 2021. This article is concerned with the two topics of fairness and robustness to noisy labels, and proposes an approach to simultaneously address two of them in a training pipeline. So let us start with the abstract. First, I provide a description of what they mean by fairness and robustness. Fairness is about learning a model that is going to be unbiased, and robustness in this case is about learning from corrupted data, which in this case they mainly refer to the corruption due to label noise. The other important thing they mentioned, which is a motivation of actually this work, is that there could be a trade-off, meaning that addressing one of these topics might have adverse effects with regards to the model's performance in the other domain. In this regard, they propose a sample selection-based algorithm that addresses both fairness and robustness to noise. They formulate a combinatorial optimization problem for fair selection of samples in the presence of data noise. And while discussing that it reduces to a strongly NP-hard problem, they provide a greedy algorithm that is efficient and in practice effective. They also conduct experiments to show the empirical performance of their proposed model. And lastly, they mentioned that this algorithm is easy to use because it only modifies the sampling step in the bias selection. Therefore, the training algorithm can remain unchanged and additional clean data is not needed. This part becomes important when it comes to comparisons with the approach called FR-Train, which requires access to an additional held-out validation set, which is clean. So that is why this component is also very important in the abstract. They start by introducing some concepts regarding fairness, and it's important that it's been attracting a lot of attention recently, and also about robustness. And they mention that their model is basically built on two recent lines of sample selection research. One is clean selection for robust training, and batch selection, which was for fairness. Now, the idea for clean selection is that in a standard approach, you discard the samples with high loss values, which are considered noisy. And the idea for batch selection for fairness, the idea is to adaptively adjust sampling ratios among sensitive groups. Specifically for clean selection, their approach is built on the model called Iterative Trimmed Loss Minimization Pipeline, which is not designed to address fairness. And now they want to show something interesting. In figure 1, which you can see here, they show that if you consider the ProPublica Compass dataset, which is a dataset that is used by US courts to predict criminal recidivism rates, you can have the sensitive attribute Z to be either 0 or 1, and you can have a label to be either 0 or 1. Now, the idea is to use the algorithm of ITLM, or Iterative Trimmed Loss Minimization, to address this and to solve this problem. Now, they show that in the case of y equal to 1 and z equal to 1, the loss that you observe is going to be highest, which is this curve over here, associated with y1 and z equal to 1. Which points to the fact that blindly applying clean selection to remove high loss samples will discard most of the samples that have the characteristic y to be 1 and z to be 1, therefore resulting in a bias against this specific group in terms of performance, which suggests that the methodologies that can help training a model robust to corruption might have negative impact in terms of fairness. Let's discuss some of what they have done in detail. We talked about the fact that there might be a trade-off between improving the performance in terms of robustness and fairness. We talked about that iterative trimmed loss minimization as a methodology specifically targeting the robustness, and it is how it is formulated like this. So S is going to be a subset of data with the cardinality equal to a ratio times the total number of items in the dataset. This is the floor operation. So this is going to be the cardinality of this, and you want to find such S in a way that the summation of the loss of all of the elements in this subset as a value is minimized. Therefore, in some sense, assuming that this measure directly has to do with the cleanliness of images or items, this is going to get you a clean subset, or approximately cleanest subset. Now, the framework they propose in this paper has three main objectives. The first one is that you want to do a clean selection with assuming fairness constraints. Two is that you want to train a model based on that selection. And third, you want to generate the fairness constraints, which renders this method to be a bi-level optimization method. The first step is to basically perform the clean selection and also assume the fairness constraints. Now consider that Z is your sensitive variable. It could be something such as race, gender, or any sensitive variable that in the specific task that you are working on, it is important with regards to improving the fairness on it. And Y is the random variable associated with the label. So first you want to generate these fairness constraints. So at this point, let's say we have these, meaning that for a specific label Y, if you sum it over Z, this result is going to be 1. Therefore, for each sensitive variable, lambda YZ is going to give the ratio of the subset of items that have the label Y that belong to the group of sensitive variables Z equal to Z. And this is going to be used in constraints in the optimization problem as upper bounds, mainly because of feasibility reasons. So the problem that is going to be defined, the objective function is going to be this. Pi is going to be a 0 or 1 variable associated with the example I. You have n examples in your data set. For each example, for each data point di, which is composed of the observation xi and label yi, you have a loss function, which is also defined by the model parameters. So you have this loss here, and you also have the parameter pi, which is whether or not to include item I into training. And you sum them all up, and you find the p, or the partition that would minimize this, or the subset that would minimize this, subject to these constraints. One is that obviously pi's are 0 and 1, and the summation of the pi, or the cardinality of the chosen subset associated with this optimal result, is going to be less than or equal to a ratio tau times n. And these are mainly for the sample selection, similar to the iterative trained loss minimization. And for the fairness, you want to do something else. For the fairness, you want to apply such upper bounds such as this. If you pick a y and z, or considering all the y and z's from the space of y and z, or labels and sensitive variables, for each one of these y and z's, if you look at the subsets that belong to this y and z, the cardinality of this subset cannot be more than lambda of y and z times the cardinality of the subset with elements with the label y. The reason why this is the fairness one is that you do not want the dominant clause to basically dominate the training procedure and lead to problems in terms of fairness for the less frequent classes or for less frequent items. The next component is training a model. In training a model, you have to note this. Given the fact that you applied the lambdas or fairness constraints as upper bounds, there is no guarantee that the cardinality of the subset with y and z is going to be equal to this, while equality is what you are actually after. But for feasibility constraints, you applied that as upper bound. So this is just something to consider. And because of that, we want to do a reweighing of these results. So consider these notations. Lambda is going to be the set of all of the lambdas associated with y and z for all of the y and z's that are possible. S of this lambda is going to be the partition or the argument that minimizes the previously discussed equation. So you have this equation. The arguments that would minimize this is a vector of p. You basically have n p's, and therefore you can essentially map it to this subset, such as this, basically the x and y's for which the pi has been selected 1 by solving this problem, which was robust and considerate when it comes to fairness. So considering the definition of lambda and s lambda, now let's see this. One thing that you do is this. In computing the loss, you want to actually reweigh that. So with that definition of lambda and s lambda, you go over the found partition. So for si, member of this, and then for all of the y and z's that are possible, what you do is that you want to consider what partition in terms of y and z they belong to, and then for each one of these partitions, you essentially sum up the losses, and then essentially, if you consider this sum, is going to be equal to this times the value and then the average value or the expected value. So therefore you want to divide this by this, multiply it by this, and time it by lambda of yz, because you want this option here to be your final result. So let's go over some of these again. So in the first step, we wanted to consider the lambda and s, we wanted to solve this optimization problem subject to these constraints, and we wanted to obtain this. Now when it comes to this component, you consider the s lambda, so basically you're iterating over the s lambda or the selected sample, and then in order to have the different y and z combinations to maintain fairness, you have this iteration over here. This part or this term helps with partitioning. This is going to be the term that is used as loss, and this is basically the coefficient that will be used for renormalizing this in order to make that equality hold. Now we get to part 3, which is how should we estimate these lambda, y, and z's. And one possible option is this sign-based negative direction of the L, y, and z prime minus L, y, and z for the z primes that are not z, and updating this fairness constraint in the next epoch based on that. For more details, please refer to the paper of Fairbatch. So let's go back to the paper. So we had this ITLM. This was the definition. And there was this discussion of blindly applying it can lead to unfairness. Figure 2 also sheds some light on this. So they have logistic regression and iterative trend loss minimization. On the x-axis you have the noise rate, and on the y-axis you have the accuracy. So generally by increasing the noise rate you would have a drop in the accuracy, but there are also the concepts of equalized odds disparity and demographic parity disparity, which results in these two cases. So in the case of equalized odds, adding the noise rate, we can see that these two that have to do with fairness, this kind of disparities would actually grow with increase in the noise in noise rate, which suggests that another algorithm is needed in order to deal with the fairness aspect of the problem. Now, how do we actually solve this problem? So the way this suggests is this. First, you consider the maximum loss and you write the optimization problem like this, and with these constraints like this. So let's for now assume that you can actually write it like this. You know that you had this constraint here before, so that one is fine. And this constraint, we're going to talk about how to reformulate what we had before in this. But assuming that we have these things, this thing would reduce into a multi-dimensional knapsack problem, which is a strongly NP hard. To see how we can actually write it like that, let's look at the formulas again. We know that for a specific y and z, if you look at all of the samples that actually would satisfy this indicator function, the summation of all the PJs is going to be less than equal to the constraint with regards to fairness for y and z times the cardinality of all the items that are labeled y. Now this is going to be the same as writing it this way. So essentially this time you sum over all of the items PIs, but using this indicator function, and I basically are 1 dyz indicates that if you give it a di and this di belongs to the label y and satisfy the sensitive label z to be equal to z value, this is going to be 1, otherwise 0. So you can essentially write it like this. And for the other way around, for the other side as well, you could write it like this. Now bringing this component to this side of the inequality and write it like this would get you this definition of w. Now the thing is, you have two options here. One case is the case where the item belongs to y or does not belong to y. And then the third option is basically based on z. So there are three types of cases. If the I does not belong to dy, it automatically does not belong to dyz either. So in this case, the value is going to be 0. We will want to add 1 to all of the values that we find later. The reason that this is going to be added is just because we want to keep these weights positive. But for now, this one is going to be 0. In a case where the label is y but the sensitive label is not z, what you will have is minus lambda yz if you do this formulation here. Again, di is going to be of label y and not z, therefore this becomes 0, this becomes 1, and you would have minus 1 times this lambda yz, and in the case where it belongs to both of them, you would have 1 minus lambda yz. Therefore, you can add 1 to this and make it the same as one you see in the paper. And this comes from the appendix. And this page has the information we discussed with regards to the mathematical formulations. Now, the greedy algorithm they propose that works actually well in practice for the sample selection component is that you consider the fair ratio lambda, clean ratio tau, and losses. You consider these terms, which are the profits. You sort them in the descending order, meaning maximum profit first, and then you basically go by the sorted indices, and if the item does not violate any constraints, you add it to the S, and once you get to the ratio that you require, you will return it. Now, in the overall fair and robust model training algorithm, you would run the algorithm for model selection. You would get S, and you would draw mini batches based on S with respect to this ratio, and for each mini batch, you would update the model parameters according to the mini batch, and then you would also update after the end of a epoch of training, you would update this fairness constraints based on the results. Next, they discuss some information regarding the hardware they used and the frameworks they coded in, and mainly about the fairness measures that they have used. One of them is going to be the equalized odds measures, or DIS, or EO disparity. The higher it is, the worse. Therefore, it means that on the spaces of y's and z's, you want to maximize this operation, and this supremum is going to be the EO disparity. And this essentially is the probability of the prediction being 1, given that z is equal to z and y is equal to y, minus the probability of y equal to 1 if you do not have the sensitive label value to consider or as an observation, and you just know that y is equal to y. And if you don't have the y is equal to y, you would have the demographic parity disparity, which is going to be this one, essentially the probability of prediction being 1 given the sensitive label is z, minus the probability of prediction being 1. As for the datasets, they have used one synthetic dataset and two real benchmarks. The two real benchmark datasets they have used have been the adult census and ProPublica Compass. And for the synthetic dataset, they had defined it based on this. They had 3,200 samples, which were consisting of two non-sensitive features of x1 and x2, one sensitive feature of z, and one label class y. They were drawing these items from the Gaussian distribution of that is shown here. The thing to note about fairness is that when they want to add the sensitive feature z, they would essentially have it something like this, and this would lead to a biased distribution with respect to z. As for the noise injection, they had label flipping and they had targeted label flipping. So label flipping can be considered as symmetric noise, and for targeted label flipping, they were flipping the labels of a specific group using group targeted label flipping. And the idea was that when they wanted to target a group, they would choose the one that when attack results in the lowest model performance on all groups, performance in this case being accuracy. As for the comparisons, they had vanilla training, they had robust only with ITLM, they had fair only with fair batch, they had fair and robust training, which was have to do with models such as the state-of-the-art method called FR-train. They also had the models, the two baselines like this, ITLM FB, meaning that you run the iterative term loss minimization first and then fair batch on the resulting clean examples. And ITLM penalty means that you first run the ITLM and then you do in-processing fairness algorithm on the clean samples. And you would add a penalty term to the loss function for reducing the covariance between sensitive attributes and the predictive labels. Now, this method, which is the state-of-the-art, has the adversarial training between a classifier and fair and robust discriminators, and for this robust training, it relies on a separate clean validation set, which renders it as a good upper bound for the performance that you would expect to get with this method, because the method discussed in this paper does not need a held-out clean validation set. And as a result, on Compass dataset, on EO disparity, and on DP disparity show, this model and the FR train are often getting the best result. And the same thing goes with the synthetic data. They also add more detailed comparisons with FR train with the assumption that consider the clean validation set. Let's say we don't have access to clean validation set, and it could be a noisy validation set. So the items are noisy val set that was cleaned with ITLM, and a clean validation set. So in the case of clean validation set, the accuracy is significantly better and the disparity is high. Now when it comes to their own method, so in this case, in theirs method, it is actually comparable with FR-train, which is the state-of-the-art, under reasonable assumptions such as that held-out validation set with clean labels is not ready at hand. They also show that in the synthetic data, their proposed methodology does not have the problem of resulting in higher disparity with increasing noise rate. They provide information with regards to the different components of their methodology as well.